Good afternoon, everyone. Today, the Robert Socolow, we call him Prof, kindly come to Kyushu University. So he gave a talk about the climate change and carbon management. So I just introduced him. He have obtained a PhD from Harvard University in the physics, right? Theoretical high energy physics. And then he moved to Yale University, and then he changed its research topic to the energy problem. And now he is working in Princeton University, and actually he has many positions, so I cannot follow the all position anyway. Honestly speaking, he is very famous in USA, and when I check him using the website, I found his face on the Times. So it's the reason why I know him is do you know the I²CNER? He's one of the reviewers of I²CNER. I visited the Princeton University at that time. He said I should meet Rob. So after that, we have communications. So I should talk many, but I hope to use time for your presentation. So, Rob.
It is a great pleasure to be with you all and to see that you are a group of students who are thinking about or going to make a major contribution to this enormous problem called sustainability. So I'm going to jump to something which was near the end and make it first. I'm going to ask each of you to decide in which quadrant you personally are most comfortable. So you have to answer 2 yes/no questions. There's no right answer. You have to tell me where you are most comfortable. One question, the top question is, are fossil fuels hard to displace by renewables, nuclear, or something else? Can we get rid of them fairly easily? And the other question is climate change an urgent matter or something we can take our time addressing? So you get 20 seconds more, and then I'm going to ask you to vote. Raise your hand. How many people are in the top left? Not anybody. I'm not surprised. How many people are over here where climate change isn't very important and fossil fuels are very hard to get rid of? Nobody. How many people are over here? Quite a number. 1, 2, 3, 4, 5, 6. This means that you think we will get fossil fuel out of the economy pretty easily, and we're very lucky that we can because climate change is a serious matter. And how many people are here? About 2 to 1 are over here. And that's kind of what I expect, although it doesn't always come out that way. There is a disagreement in the world right now, maybe more than even 5 years ago, about whether we can fairly easily close down the fossil energy system. And that's kind of the important question that is driving my thinking and this talk. Who would be in those 2 quadrants? It used to be that there were quite a few people, say 30 years ago, had never heard of climate change, but they were convinced, especially nuclear people, were convinced that coal power plants would be shut down because nuclear power plants were so much better, and similarly for other systems. A lot of people in the fossil energy industries are here, and a lot of the public is here. Don't bother us with climate change. Something else will take care of it. We can't really look at how big the sky is. We can't be changing the sky. And so fossil fuels are here, and that's okay. None of you was in that box. Here, I'm going to use the words here that I'm going to spend the time explaining. But here are the people who are also comfortable with the world because we have a big problem, but we know how to solve it pretty easily. And here are the people who have trouble sleeping. People have trouble sleeping. That we really have two problems that are inconsistent. We have a terribly difficult problem, and we don't know. We have a terribly difficult problem. Climate change is very severe and urgent, but we can't really easily get rid of the fossil energies. All of you have in mind that in this room, people voted in substantial numbers for both of those two quadrants. I'm using two words here, AirCCS and FossilCCS. Those are not normal words. I made them up. And I go to my first slide, say, what do I mean by that? CCS is carbon dioxide capture and storage. It's got two versions today, one of which is much newer than the other. And this particular graph comes from a recent IPCC report. I'd never seen a graph like it. And so I kind of find it very helpful. So this is out to, I think, 2100, and it's a typical scenario of how much carbon dioxide will be emitted by a certain period of time. This is now, and lo and behold, we reduce the amount of carbon dioxide a lot by various strategies. This says this is buildings and transport and industry all going down. But there are two contributions that are in brown. This is carbon dioxide that doesn't go into the atmosphere because fossil energy is being burned, but the CO2 is being captured and presumably put into geological formations. And so it doesn't actually go to the atmosphere. We just keep track of it in this picture. Also, and starting a little later, we have another activity called taking carbon dioxide out of the air. And it gives us negative numbers. Here's 0, and so we have a contribution here. This other one here is land use. But these two, this one and this one, are the two kinds of CCS that I'm talking about. And jumping ahead, I have spent time on both. I ran two different meetings, 14 years apart. One of them was on this guy first, and then later on this. And for your community, I'm asking how we distribute our effort, how you spend your time, which problem you choose to work on, which problem, and then if you're a politician, which programs you support, in what ratio. And my sense is that this community that some of us older in the room are part of, and that you are joining, is not actually asking this question of itself very clearly right now. And that I want you to talk among yourselves after this meeting about the very question of where do these two things fit together. An example of the first kind of CCS, fossil CCS. You may never have seen this particular power plant, which is the only CCS project at large scale in the United States and one of the few in the world. Started about 5 years ago. This is a coal power plant in Texas. It's very large, it's I think 3,000 megawatts. One of its systems, burning, which is a 650 megawatt power plant, has a slipstream. The CO2 is being taken out of the flue gas with a amine capture system, which is this guy over here, and the CO2 is being removed and piped away actually for enhanced oil recovery about 100 kilometers away in a pipeline. And all of this is working right now. It wasn't, and it has, they actually built a separate natural gas power system to run it. It's a demonstration project for fossil CCS. The idea is that maybe all coal plants built from now on would have CCS, maybe all natural gas plants would have CCS. This would be the normal way to have a coal or natural gas power plant. It would be more expensive, but it would protect the climate. An example of the other kind of AirCCS is this. This is a small pilot project on a roof in Switzerland near Zurich. I've actually been to both of these places. I went to the groundbreaking. I went to the groundbreaking of this project. It's very exciting, but they've got it started. I forgot to mention, there's a major Japanese contribution to this project, Mitsubishi. And the groundbreaking it started with a dinner. And do you know that when the Japanese companies have a big event, they bring barrels of sake and hammers? How many of you ever heard of this? I'd never heard of it. But to build a lot of spirit, you know about it. So you want to explain it, Jeff? So they have these hammers, and they're 6 people who are big shots, executives, all hit the top of the sake barrel together. So that was going on the night before the breaking of the ribbon and getting it all started. So the Japanese have a major role in this project.
So most of the plant made by Mitsubishi in this project, the capture part.
The capture part. This part. Yeah, the plant was old. The plant was built quite a long time ago. And this was added with Department of Energy funding. This is very new. It's a company that is capturing CO2 from the air. I was there 4 weeks ago after a meeting that was about CCS that was held in Switzerland. It's about a 1.5 hour train ride from the center of Zurich. You get there and you walk down a street. And we went up there with the man who's in charge of a new company called Climeworks, on top there. This is an 18-unit assembly over here. There's another one, I think, with 12 units over here. It's most of the ones it's a large fraction of the ones that exist altogether. He has a special sorbent, which absorbs CO2 at lower temperature and removes it at higher temperature. And each unit would take 50 tons of CO2 per year out of the atmosphere if it was running continuously. And its particular feature is that it regenerates the sorbent at a relatively low temperature, 90 degrees Celsius. So it turns out it uses a lot of energy to make it run, and I'll talk more about that later. But it seems to work. It's been running for 2 years, and people are very excited about it. Which of these is going to be commercialized first? We've got a pilot project in Texas, and another few around the country, around the world. There's another one in Canada. You have a small one in Hokkaido, I learned. AirCCS, just a few projects starting. I would say a year ago or 2 years ago, no one thought this was an interesting question. Of course, FossilCCS is going to be started. Fossil fuel CCS motivated this whole field. It motivated because the idea was we're in the bottom right quadrant. We can't get rid of fossil energy. It's here to stay. It's very attractive. But we want to protect the climate, so we'll add CCS to the fossil energy system. That was what was driving the CCS program of the world. Along comes this new guy, air capture. Could it start things? So I've asked, I'd like you to talk this through yourselves. This is a new slide. I mean, I've not heard anybody ask this question before, so I made a little list. Fossil CCS would come first because the oil and gas industry knows how to handle the CO2, any fluid below ground. And so it would be more likely to want to take care of a fossil carbon CO2 than an air CO2. And so they've always been thinking about doing this. They have a lot of experience. 20 years they've been thinking about it. And if we do it first, we will get low carbon natural gas and coal power plants rather than the ones we have right now. They're big so that there's scale economies in the cost. And this one I'll talk about again. I'm going to use the phrase net carbon many times today. It defeats air capture and storage. I'll talk about what that means again. But on the other hand, people like air capture. It's amazingly popular. They say, we have too much CO2 in the air, take it out. So maybe it'll get subsidies, big ones, and people will do it. And maybe the oil and gas industry will actually say, okay, if that's where the CO2 comes from, I'll take it. I'll put it below ground. I have geologists and reservoir engineers, and I'll put this together. It's decentralized, it's on small scale. You saw that 50-ton per year unit. So we can make millions of them. Maybe like solar energy, it'll get cheaper because it's modular. And by the way, fossil carbon capture isn't going to happen. It's a mindset. We have wind and solar now, and the story of fixing up CCC coal power plants, that's history. That's your generation, Professor Socolow. It's not the generation in the rest of you in the room. It was a silly idea. We could do better. So I think that's an interesting debate, which I'd like to encourage you to have. These slides are already circulated, and you can see them again, and I hope you'll talk about it. I don't know the answer here. But let me give you a few thoughts about FossilCCS. I wrote an article in Scientific American in 2005, at the request of the journal, called Can We Bury Climate? It's called Can We Bury Climate Change? Bury meaning put it underground. Can we bury climate change? And this was the figure that was, I think, most interesting, that was drawn by several people that was in there. We kind of, number of people, I was the only author, but a lot of people who cared about this subject, helped me and discussed what should be here. And I've seen almost no graphs like this. A coal power plant that was 1,000 megawatts will produce about 6 million tons of CO2 a year. Depends on how the efficiency of the power plant and the capacity factor, but it's at peak 6 million tons a year. Now I've got to put that underground. It's going to be supercritical CO2. It has a certain density. My question was, how much physical space will be required to put that CO2 underground? And this is an answer in the form of a picture for these guys here. We call them lily pads, flat pancakes, was the CO2. And that would be the area that would be required, provided we had to assume a vertical depth, 60 meters vertically, altogether actually in 2 formations. And we had to assume an answer to a geological question, which I know is not simple at all. What's the fraction of the available? Well, first the porosity. Then what's the fraction of the pore space that CO2 can actually occupy when you're clever about how you put it in? And if we guessed a very high number, actually 1/3 of the pore space, it might be much less than that. So you're a reservoir engineer. Your job is not to take up too much space below ground, because, by the way, there may be another coal power plant over here, and you don't want them running into each other below ground. So this question is actually pretty interesting. And our thinking was, this is the future. Coal power plants will have space below ground dedicated to their CO2. And by the way, the other question was, how long has this power plant been running? In this particular picture, we said it's been running for 10 years. It's probably going to run for 50 years, so this is not the end of the story, but this is just an intermediate picture. By the way, am I understandable? First of all, can you hear me? Second of all, do you understand me? Because I'm talking maybe not quite, maybe a little too fast. If I should slow down, it's time to tell me. How are you doing on comprehension? You don't hear that many lectures in English. How are you doing? Slower? Should I talk slower? Louder? No, quieter? What does this mean? More slowly. Okay. Do you follow? Do you have a particular question for something already? Not yet. Okay. So the kind of question we were asking 15 years ago, 10 years ago was, is this the wave of the future? How soon can CO2 capture and storage be required at all new coal and natural gas, should add, and natural gas power plants? You can read these words. So the idea was, this is really, really important because we're in that bottom right quadrant. And suddenly we have a new question. So I'm going to skip this for now. We have this question, AirCCS. And my finding is that the community that used to think about the first problem is beginning to think about the second as if the first problem was taken care of already. But there are just a few projects, one small project in all of Japan of the other kind. Anyway, let's talk about AirCCS. And let me recommend that you memorize this is the number I have in my head. You can work it out and check me, and then memorize. If I have a square meter of area through which air is flowing, imagine it's about the size of a window, air is flowing at 2 meters a second, which is a typical velocity for the game, and I capture half of the CO2 in the atmosphere as it comes through. These are the only inputs I need to discover that I will capture 20 tons a year. So 2.5, 20. You can scale everything from that you have to use the density of air and molecular weights and a few other things to make that calculation, which all of you know how to do, and you should check me. So and the average American used to emit 20 tons a year, that number, now down about 15. It's actually gone down. The average Japanese, I think, uses about 10 tons per capita. So one of these would take care of 2 Japanese. A husband and wife own this one square meter machine. They carry it around with them. Well, they're running it all the time in their backyard, and they're breaking even. They capture as much CO2 as they're emitting. They have to do something with it, of course. That becomes another problem. This is helpful because you can't. This sets the scale. And by the way, for that Climeworks system, I told you that was 50 tons, and it is about, that opening is about 2 square meters. So the numbers kind of work. Okay? So the report that I was part of was pretty pessimistic about the cost, always driven by the fact that CO2 is only 400 molecules out of 1 million air molecules. So a lot of air has to go through. And when we were working out the costs, I realized that sorbents like the one that's used in Climeworks, that the cost math, the mathematics for costs, was actually driven by a pretty simple idea, which I call the 3-factor formula. What have I just done? Okay. The capture cost turned out to be the most important cost in many calculations, was the cost of the sorbent itself. It was an unusual material, so it was not going to be so cheap. And it might be a fragile material that didn't last very long, easily falling apart. So if I know its cost in dollars per kilogram and how much CO2 is captured in one cycle, going absorption, desorption, absorption, desorption, And if I know the sorbent lifetime, how many cycles before I have to replace it? That'll tell me the cost, dollars per ton of CO2. So for example, if it costs $10 a kilogram, 1,000 yen, if I can get 20 kilograms of sorbent, in one cycle, I need 20 kilograms of sorbent to take 1 kilogram of CO2 out, but it runs for 4,000 cycles, then it will cost me $50 a ton of CO2. 4,000 cycles, it might be a 1 hour cycle and half a year. The Climeworks cycle is actually 4 hours long. So it would be 2 years before I had to replace it. And then I get this number. And we thought it would be extremely difficult to find a good sorbent, but that's what chemists are trying to do. A point about air capture that I think is very important. People love it. They say, well, just take CO2 out of the atmosphere and climate change will be solved. It's an enormous enterprise to reduce the carbon dioxide concentration slowly. And to do it fast is close to impossible. So if I have an emergency, I discover that I really want to, the climate is changing, I didn't expect it, glaciers of ice is falling out of Antarctica just into the ocean and the sea level is rising. Can I use CCS to solve the problem? The answer, I think, is no. But I should think about AirCCS as perhaps reducing the concentration of CO2 in the atmosphere by 1 part per million per year for 100 years. So I start when it's 450 parts per million, I get the whole world works together, we get it down to 350 in the middle of the 22nd century. That's important. It's possibly what we'll do, what the human beings will choose to do. And that would look like this, where so this is we want to reduce by 100 ppm. That is 750 billion tons of CO2, approximately. This triangle has 750 billion tons of CO2 in it. It says in the first year we take out 0.2, and we climb all the way out here. And by the end of 100 years, we're taking out 15 billion tons of CO2. Now that's not maybe ambitious enough. Maybe that's not that, but that isn't so far from what I²CNER often puts in. This would be response to a crisis. We're going to take that much out in 10 years instead of 100 years, but the same amount removal. The slope is 100 times bigger because the vertical is 10 times bigger and the horizontal is 10 times smaller. And that would mean that in the second year we were taking out But we're taking out it's 10 years. So the first year we're taking out 15 billion tons. The second year we're taking out 30 billion tons. 30 billion tons is almost the whole emissions of the planet right now. We're reversing that all in 2 years. That's a scale of effort that's pretty hard to imagine. So AirCCS is not matched to emergencies. On the other hand, there's something called geoengineering in other kinds, putting particles into the atmosphere on purpose that maybe is a fast response system. We'll comment to both. I want to talk about this concept of net carbon. Not much appreciated. In the Climeworks system or anything like it, we're going to have to get the energy to make the system work from somewhere. Suppose we're going to get the energy from natural gas. And suppose it takes 500 kilowatt hours to take 1 ton of CO2 out of the atmosphere and put it below ground. If I use 500 kilowatt hours, I will put 250 million tons of CO2 into the atmosphere just from the natural gas. So I'm getting 1 ton out, but I'm putting 1/4 ton in. So I'm getting only 3/4 net. Am I talking okay? Or it's still too fast? 3/4 net. So I work out the cost to say be $300 a ton. When I'm talking about the CO2 just going into the ground, that's $400 a ton net. So there's a factor of 1 over 1 minus x in the problem, multiplying the gross cost to take into account the emissions to the atmosphere. Why does it look like, why does it look like 1 over 1 minus x? What is x equals 1? If x equals 1, this is infinity, right? So why is this factor, what does x mean if it can go to infinity? It means that if in the process of taking one CO2 out of the atmosphere, I'm putting another one back from the energy system, then I'm getting absolutely nothing accomplished, and the cost is infinity. X can be even larger than 1, and then I'm putting CO2 into the atmosphere while I'm running the system. So X is very important. It turns out that, again, because of the dilute character of CO2 in the atmosphere, it turns out that it's not so easy to make X small. And the Climeworks system needs a lot of energy. So there was a graph that was shown in a meeting that I went to, where the question was, what is X? It depends on not just how much energy we're going to need, but how carbon intensive that energy is. And so this was a graph which looked, this axis was how carbon intensive is the energy, and this was the carbon demand. It was a diagonal line, and there were different countries. If you were Norway, you used almost no carbon. You put almost no carbon in the atmosphere when you needed when you used the electricity. It wouldn't be 500 kilowatt hours. It might be 50 kilowatt hours. If I was Germany, I might have an energy system of that bit like natural gas, balancing out different energies. U.S. is about like that number. The energy system, the electricity system, average of the whole country is about 500. In your country, it may be a little higher than that. Of course, in different parts of the U.S. and different parts of Japan, the number differs. In the northwest U.S., as you may know, which is where the hydropower is, we are like Norway, and so forth. So it's a very important concept, is how much carbon is going to be required. And it makes me say, be careful with this excitement about air capture if the energy system you're going to use to make it work is carbon intensive, if it's based on fossil fuels. Be careful, you actually might put more CO2 into the atmosphere than you're taking out. In some extent, the air capture idea belongs to a period of time in the future when we've already closed down the fossil energy system. That's a pretty strong statement. It's not being brought out by the advocates of direct air capture immediately. Let's get on with it. Let's do it immediately. If we're not careful, we'll actually be running a pretty stupid system. Now, what do the air capture people say at that point? They say, well, I'll go to a remote location, like the middle of Hokkaido somewhere. I will put an air capture machine there, and I'll build a hydro plant or a wind system to power it. And then I won't put any CO2 into the atmosphere for the energy to make the direct air capture system work. And what's the counter to that? Well, if you're going to build that hydro system or wind system, use it so that you can close down one of the Japanese coal power plants that's running right now. Use it instead for backing the other, an old system, a fossil energy intensive system out. That's called in economics the opportunity cost. What did I not do? Because if I use this for air capture, I could have used it for something else. So here's this graph of 1 over 1 minus x to remind you what it looks like. It goes to infinity, of course, as x goes to 1. If I'm over here, penalties are not so bad. If I get over here, it's pretty terrible. Now this is the opportunity cost argument. So do you follow this opportunity cost issue? The CCS really, AirCCS really requires low carbon energy, and there has to be a lot of low carbon energy around, or the next low carbon energy could back out some existing, replace some existing high carbon energy. I know that some of you work on enhanced oil recovery, is that right? Who works on enhanced oil recovery? Nobody? You told me some people work on enhanced recovery. Not directly. So some of you know that carbon dioxide is being used in the industry today. And the number one industry that uses carbon dioxide is the oil and gas industry, which is interesting. So I'll take a couple of minutes and the United States has more of the enhanced oil recovery than any other part of the world. First, this is something we built mostly about 30 years ago. We were worried about importing oil. We wanted to make more oil from our domestic oil fields. And we knew that carbon dioxide is kind of a special molecule below ground. The same I call it the miracle molecule below ground and the mischief molecule in the atmosphere. Below ground, it combines with oil, physically and chemically, to make oil move more easily, lower its viscosity. And then it can be, more oil can be pulled out of the same formation if you use CO2. You first use steam, that does some job, but more of it with CO2. So the oil industry pays to have CO2 delivered to an oil field, especially after it's been running a while, a few years, and it gets more oil out. So it's ready to pay for the CO2. And in the United States, these locations, these yellow places over here, there are 5 of them, maybe 6 of them. Now that's different. These 5. These are natural CO2 fields. Below ground, there's a gas, just like natural gas, except it's almost pure CO2. Strange. Who knew there were such places? And because of a US tax policy, it was worthwhile to build a pipeline about 800 kilometers from here to here and take CO2 out of the ground that would never have come out of the ground by itself. Take it all the way down here and put it into oil fields in what's called the Permian Basin. And they connected these 3 fields, and there's another similar situation going on here. All of these would never have brought CO2 out of the below ground. So we were paying people to develop CO2 fields at a time when we were not very much worried about climate change. The oil industry will tell you that hardly any CO2 leaks. It comes out of here and it goes back in there, most of it. So we're not making the climate much worse. But we could instead be capturing CO2 from power plants all over Texas and Oklahoma, and all over here, over there, that would have gone to the atmosphere. We put that below ground. So that we now have new policies in the United States to say, we'll stop subsidizing this, we're subsidizing something else that is fossil CCS. And that's one of the things that we have a new policy in the United States to stimulate fossil CCS and to try to make, but these are still running. 30 years into this story, they're still running. How do we think about putting CO2 below ground into places where there's fossil energy was taken out? I like to think of it like this. There's an oil, here's the carbon molecule, and it comes out of the ground approximately with 2 hydrogens attached. If it's oil, it's more like that, CH2. So they're little guys, these hydrogens. Little kids coming along. Then I go back underground with these big oxygen molecules, like 2 bodyguards on my 2 sides. We don't fit in the same space we came out of. We need about 3 times the volume just to get back in. So the enterprise of CCS involves enormous volumes of supercritical CO2. We can't, and so it's really daunting. The size of the enterprise of fossil CCS or AirCCS is dramatic if we're going to make a difference in climate. We're talking about an industry as large as the global oil and gas industry, or even bigger. in terms of quantity of fluid managed. If there's any real limitation, it's the scale of the enterprise that is really daunting. We probably have enough space in porous space below ground, in a lot of places. We might carry the CO2 in ships across oceans, but it's an enterprise of dramatic scale that we're talking about in this room that a few people work on. Most people think it's never heard of it. Most people never heard of it. Those who heard of it think it's very strange. But we in this room are talking about maybe this is a serious contribution to climate change. So I've shown you these two already, and I'm going to jump through that so we have a chance to talk. I like to talk about something called destiny studies, my last slide. We don't use that phrase. You guys are going to have a 50-year career that's starting around now. What are you going to be worrying about? Pretty much new things that previous generations of young people did not think about. My generation did not hear about sustainability when we were your age. And then there was a generation of my professor friend here that's halfway between you and me, and they learned about it in the middle of their career. What's this about? It's about, at one level, it's about 7 billion people living on a small planet. If our planet were the size of Jupiter and had a nice atmosphere, which happened to be in Earth's orbit, but was the size of Jupiter, we would not be talking about any of this. We would be happily using everything we had. It's the confrontation of active species, us, with lots of interests, lots of desire to travel, lots of desire to have nice houses, and a planet that just isn't all that able to absorb what we do. Now, some of that can be affected by choosing different technologies. Most of those technological choices will have their own consequences, which are also expressing the fact that the planet isn't very large. You start covering the planet with solar panels, you use lots and lots of land. You start managing the planet with forests, you realize you're using almost all the world's forests. Over and over again, the way we're eating, and the agricultural land, the way we use water, over and over again, we are confronting the fact that the planet isn't large compared to our appetites and their impact. We're going to figure this out. We're not going to disappear. We're going to work very hard, and your generation is going to confront this dilemma and figure out solutions for your whole career. Probably your children and grandchildren will also, but you're the first generation who has this set out for you at the front end of your career. That's what I'm going to write in that little note that you want. So what did I say here? Let's give it a name. Let's imagine a new department. Let's imagine a building on the Kyushu University campus that isn't there right now. Built pretty soon to express a new curriculum, which has some of these thoughts in it. These are not familiar thoughts. These are not the thoughts your professors have spent a lot of time thinking about. We have lots of old patterns. It's about our collective future as a species. Who thought about that before? Show me writings from, let's say, 1950, which talk about our collective future. Show me religious traditions that talk about our collective future. All of us, as opposed to some of us. Some of us going to heaven, some individuals going to heaven, some of us being reincarnated. We don't think about the whole living species continuing through other generations and what kind of future we're trying to create. This is fresh stuff. We're part of it. Some people say, okay, so humans are going to live another generation or two and then it'll all be over. Some people say that. And if everybody dies quietly, it's okay. Human beings will be over. We're creating a lot of trouble for other species. Let them have a chance. will get out of the way. That I really reject that. But some of you may not. If you do, then you're saying we have an obligation somehow to the universe to stay in business. We may really be an absolutely unique experience in the universe. Maybe, we don't know otherwise, there isn't any other intelligent life. Everybody's convinced, well, there's going to be intelligent life. Maybe there isn't any. We don't know that there is. So maybe we're the first experiment ever in the universe to understand the universe. At least that's one of the reasons I think we should be around for the long term. And some of the smartest and most caring young people on the planet, including the people in this room, which is why I wanted to come and talk to you, find carbon and energy problems exciting. That's why I'm optimistic. So I'll just quickly show you the two, just as acknowledgements, people who participated in both of these are on the web, the workshop on fossil energy carbon at the Department of Energy in 1997. I put a red box around Robert Williams, who's a colleague of mine who led me into this subject and always was a step ahead of me. And then the air capture group, which was 2011. This case for the Professional Society of Physicists, called the American Physical Society, publishes Physical Review and other things like that. So thank you.